Hello, good evening. My name is Greg Shay. I'm with the Telos Alliance. And what I'm going to talk about today is practical experiences and experience with PTP. And you could also call it dirty tricks with PTP or under the covers with PTP. And let me explain why I came upon this subject. Of course, PTP is the foundation of all of our media over IP. At Telos, we developed Livewire about 20 years ago, and I was about 2 years ahead of PTP. So if it would have been around, I would have used it, but it didn't exist. So original Livewire sync actually turns out to work very much like PTP with a couple of differences. But that has given me insight on how PTP works and what it's doing under the covers, and to understand some of the other variations that are not as often talked about. So on the agenda, my topics, and I just had a conversation in our booth that the gentleman exactly asked me 3 out of these 4 questions. So I know there's probably people thinking these things. Do you always have to use a GPS referenced PTP master? And if not, when? When is it safe to not use a GPS reference? Are using PTP aware switches always necessary? They're obviously called PTP aware switches for a reason, but do you always have to use them? Can you safely not turn on the peer delay request and response mechanism? And when? And what does that mean? And then finally, if I have time, and I don't have a clock, somebody's going to have to give me the signal. Okay, there it is. Just a little word about when you're designing equipment, does it matter the internal oscillator, which you're using, and how does that relate to PTP? So let's dive in. Yes, AES67 and PTP work if you don't have a GPS reference. It's fully legal. PTP knows about it. It's called an arbitrary clock, which means you don't know what time it is. You don't have a reference. It's one of the lowest categories of the best master selection algorithm. So it's always going to lose if you actually have another master that has a GPS reference. But it can be done, and it does work. When can you use it? Because that sounds like a pretty scary thing. Well, the point is, if you know you're on a closed LAN, or you're in a self-contained facility where you don't need to send or receive AES67 streams outside that facility, then it doesn't matter, because all that matters is everybody is on the same clock. Doesn't matter if it thinks it's 1970 or not, it works. Now, what we do is in our products and our X nodes, we build in the ability for them to be a PTP master. But when they are, they don't have a GPS reference. And so this is the mode they operate in. So it's very convenient for demonstrations, for here at the trade show, if we didn't manage to get a GPS antenna on the roof. But you have to know when it's safe to use that mode. So here's a couple of these quirks. And does this show up on the screen? I don't think so. I mentioned that systems don't care whether it's January 1st, 1970, but actually the standard open source PTP for L, the PTP for Linux client, does care. It doesn't work. You have to get at least to about January 2nd, 1970, and then it starts to work. So there's a simple fix for that. When you have a device that fires up, you just set its default to, sometime like last year or this year or whatever. Pick something other than, and I think the reason is, if you're too close to the origin, I think some of the math then probably goes negative, and that's not a case they ever tested for. People might say, well, why can't I make a PTP master and then use NTP to give it to time? It doesn't work. It doesn't work very well because 2 things. NTP is generally accurate to about 10 milliseconds. But that's not really the problem. The problem is that NTP then also wanders around. So the fundamental accuracy of NTP is not high enough to ever give you any precise number, even if it has an offset. So it generally doesn't work. We tried this early in Livewire, and if you wait long enough and filter out the variations long enough, you can get it to settle down. But we calculated something like it would take 2 weeks to filter out NTP to be stable enough, so it's not usable. So I basically already said this, got ahead of myself. The thing you want to think about, and many professional broadcasters, of course, are operating with streams in and out of the building. So it is just a very specialized use case. So here's a question. Can you then just send the PTP over the WAN if you're operating remotely? So if you can get multicast routed, technically you could. I hear rumor that the newer revs of PTP will have more of their unicast PTP variation spelled out. But the point is, when you do that, it's always going to be somewhat less accurate because there's always more jitter over a WAN. And then everybody has to fight to reduce that jitter. And really, in practicality, you're better off putting a GPS receiver at each location. And that's what I always recommend, and that's what we recommend. Okay, are PTP-aware switches always necessary? Okay, so to answer this, I have to talk about, to give you a perspective of what is the magnitude of the phase accuracy. Because what happens, peer delay request and response, what that's doing is compensating for the network delay between you and the grandmaster. So, it sent this clock packet with a very precise nanosecond time, and it's going to take something like 10 or 20 microseconds to get to you, depending on the network. And the peer delay request is a mechanism of finding out, basically by pinging back and forth, okay, what is that delay between me and the grandmaster, and then compensating for it. I am talking about the wrong bullet point. So I'm going to go ahead and do this, and then I'll go back. Sorry about that. So, a couple things to realize. If you don't use the peer delay response mechanism, it means you're basically going to be behind by some tens of microseconds, generally. The RTP timestamps are not affected. Those are still good. So if you're trying to receive multiple simultaneous streams and phase align them, you still have that information. But it basically affects where you're going to then reproduce out to analog, okay, so microphones and speakers. And what it translates into is a time error of the reproduced sound, for instance, coming out of the speakers. So what does a couple of tens of microseconds mean? Well, one sample at 48 kilohertz is 20.8 microseconds. So we're talking about a couple of samples of phase error. And what does that mean in space? So if I have my head and I'm trying to listen to, a perfect stereo image, and I move my head by a quarter inch, oh my God, I lost my stereo image, right? No, you can't hear it. Now, it depends on your application, okay? So only you can decide, but again, I'm trying to give that perspective about what does it mean. So the point is, at least for our use cases in radio audio, it doesn't make a difference. You can't hear the difference. It doesn't make a difference if we turn off PTP peer delay. And this, again, is part of our experience in the past because Livewire Sync did not have that mechanism. So we have 20 years of experience. We have never had a situation where it made a difference. Now, so here's a couple of points. It's legal. I looked carefully through the PTP spec, and you are allowed to turn off peer delay requests and response. It's not really a hack, it's just a choice. And that's my point that I'm talking about today. Some of these choices less taken. It does say if you're going to do that, you should basically declare that in the PTP profile. So if you're not all of a sudden going to do it, you're supposed to let the situation know. But you can, that's my point. Now, here's the real kicker, and the reason why we turn it off a lot of the time. PTP peer delay can actually work to make audio worse. And that's what I'm going to explain. The reason is, remember I talked about you can't hear the difference if you move your head or you move a speaker by a quarter inch or more. If it's moving around, if your phase delay is unstable, that you're going to hear. You're going to hear if it's unstable. So the point is, as you're recovering time for your audio reproduction, like in your DDAs to your speakers, using the clock synchronization is one source of error. The peer request measured at the other end is another source of that error, and then the response has its own error. So what's happening is using, so this is just a diagram of what's going on. You have the initial transmission of the sync packet, and then the slave sends the delay request, and then you get the response back. It's bad enough, and you're working hard enough to recover the clock accurately from the. Think of jitter in the time of arrival of packets as time noise. It's a random variable like noise, just like we've dealt with noise in audio, but in time. And so the point is, if you have 3 noises added up, you end up in terms of an overall magnitude that goes by the square root of the number of sources of noise. You're, square root of 3, there's more noise. And you can't get rid of noise. So this contributes to the clock being less stable, wandering around more. If you turn off the delay response request, you have an absolute error of a few tens of microseconds, but it's potentially more stable. So now I'm going to go back. Sorry I skipped. It's been a long show. About the PTP aware switches. It also has this phase accuracy question. So, how does a PTP aware switch make the recovery of sync better? And because what it does is basically when a clock packet comes through it, there's 2 mechanisms, either a boundary clock or a transparent clock. It basically fixes up the timestamp in that clock packet according to how long it took to get through the switch. So you're getting less error, less time noise, by the time you receive those clock packets. Now, to partly understand how bad is it if you don't have PTP-aware switches, it helps to understand where the delay through a switch comes from. So the main source of where clock packet jitter is coming from is this thing called the priority inversion, even if you have quality of service turned on and configured correctly. If you don't have QoS configured correctly, that's the first thing you should do, is make sure you have it configured correctly. According to AS67, the clock packets are at a higher level than the audio. So they should be coming through right away. And there aren't that many of them. So there really isn't a traffic or congestion problem. So if your QoS is broke, fix it. So with QoS operating properly, priority inversion is this. What you expect to happen, the red is the high priority, and sync packets are pretty small. The blue represents a full-size packet. Something, whatever. Somebody's transferring a file, it might be media, whatever. You expect the red coming out to go through first. So here's the race condition. Even with QoS turned on, if that high priority packet gets there just slightly too late, and the big packet already started to go out, it has to wait to the end. I believe in the early days of Ethernet, some people experimented with, cut-through switches that would interrupt this one, let that through, and then restart that. But in general, our general switches aren't doing that. So this delay, this was supposed to be high priority, but it actually got late by that amount. So the formula is this. The maximum quality of service priority inversion delay, so what is this delay? This is the size of the packet, like a full-size Ethernet packet, 1,500 bytes, how long it takes to go out your wire speed. So obviously 100 base T is slower, gigabit is faster, gigabit is about 25 microseconds, 10 gig would be 2 microseconds, times the number of switches that you've gone through.
Isn't the switch smart enough to know that it delayed that packet by that amount?
Okay. Okay, I'll repeat it. He said, isn't the switch smart enough to know? And this is the difference between a PTP-aware switch and not. That's the point I'm trying to make. A PTP-aware switch would know this happened and fix up the timestamp here, so you wouldn't have this error in the timestamp. This is the difference of not using PTP-aware switches. You get this kind of error in your clock packets. Thank you for the question. I could have been more clear on that. So here's the punchline. It is possible to process your synchronization and filter out this kind of jitter at the device end, okay? And I refer here, well, what you do, the answer is, and I think this is probably the first time I've talked about this in public, but you use a statistical minimum filter, which means you are looking at a set of synchronization times, and the one that got through with the least delay is the one that wasn't delayed. So you basically find the ones that got through with the least delay and ignore the others. That's the statistical part, and you just use the minimum one. I tried to patent this. I discovered this myself in 1999. I literally dreamed it and woke up, thought I had a solution. And the darn patent examiner was bright enough, actually the European guy was. He found it in NTP 2.0 from 1989. So you can go look it up and you can see, you can learn about this. And I'm amazed, I've kept really quiet about this for 20 years and I don't see many people talking about it. So you can effectively make your PTP synchronization recovery better by doing this kind of synchronization. And this is just a picture. When I went back, 18 years ago, looking for this paper that I saw back then, I remember this picture, and that's how I knew I found the right one. And when you understand this picture, you'll understand the whole process. So I'll let you go look it up. Basically, this is saying the packets that got through with the least amount of delay didn't have this jitter, this noise. This is jitter. So what you're doing is this is your set of data, and you're just using that point right there, and it doesn't have any jitter in it, and thus it's you've separated out the noise. It's a cool trick. It really works. Okay. I guess I talked fast. So my last point is this is kind of a hardware design thing, but it's good to know about. You learn by your mistakes, right? So about, let's see, when was it? 1994, I was designing video codec equipment, and we were selling it to British Telecom. And this is actually some of my background in clock recovery and all that, because I had to write software phase lock loops. And PAL Video in the UK, if anybody knows, is very much stricter on its color subcarrier than never twice the same color. I dubbed PAL Problems Are Lurking, because I can't tell you how long it took me to debug the darn logic. It's a complicated timing structure. But anyways, I had to recover a clock. They have a spec of 0.1 ppm phase drift per second. So I could hit the accuracy, but I couldn't get that drift down. And it turned out what was going on, okay, so this applies to PTP, so this is the moral of the story. What you're always doing is you're using this information from the clock sync packets, filtering them, processing them. Typical rates are, there's a default of 1 per second, and it's better to go faster for faster synchronization. They can go up to 128 per second. But you're always using that information to steer your local oscillator. And you're trying to make that local clock match the grandmaster. You've got these time delays that we've talked about. You've got the noise getting in the way, creating instability. Well, here's the problem. If you're trying to steer, to match this grandmaster, which is very accurate, and your local oscillator that you're steering itself is unstable, and it's wandering around, what happens is you're trying to steer out its wandering around to match something that's very stable. So the point is, if you just use a typical garden variety crystal, that, typically they're 50 ppm tolerance. What you don't realize is they're wandering around maybe like 10 ppm. And so this is this lesson that I learned, that this equipment up in Scotland, where it was cold in the winter, somebody would open the door to this, equipment shed out in the wild. The cold air would come in, hit my oscillator, and it would react and knock the PAL out of sync. It wasn't anything to do with the sync algorithm, it was the local oscillator. So I learned about temperature compensated oscillators. And typically you can buy one. They're about 2.5 ppm tolerance. Temperature compensated, they don't wander around very much, and they cost $1 or $2. So that's my point, is when you are implementing your own equipment and doing PTP recovery, do yourself a favor and start with a stable oscillator. And that's about it.
Just out of curiosity, is everything? How much of the equipment that you produce today is AES-67 versus prior technology?
Sure. So everything we produce today is AES-67, and that's designated. Our trademark thingy is this LiveWire Plus with AES-67. Yep. That's what that means. And so all the audio streams, everything's fully compliant AES-67, but first of all, we keep our backwards compatibility, with our older gear. But the LiveWire also refers to our control protocol and our own advertising discovery protocol. But we're all in on standards. So, we've added SAP, and we've got, the NMOS and ISO4.
Good.
It's just where we aim. So
excellent. That's great to hear. Okay. Well, thank you very much. That concludes our theater for today.